Question number 11. In any 15-minute interval, there is a 20% probability that you will see at least one shooting star. What is probability that you see at least one shooting star in the period of an hour? To determine the probability of seeing at least one shooting star in an hour given a 20% probability per 15-minute interval, we can use the complementary probability approach. The probability of not seeing a shooting star in a 15-minute interval is 1 minus 0.2 is equal to 0.8. Since each 15 interval is independent, the probability of not seeing a shooting star in 4 consecutive 15-minute intervals equivalent to an hour is 0.8 to the power 4. That is, we multiply 0.8 4 times. So that would be equal to 0.4096. Therefore, the probability of seeing at least one shooting star in an hour is 1 minus 0.4096, that is equal to 0.5904, that is 59.04% probability. Please note that this calculation assumes independent between each 15 interval and it is based on the given probability of 20% per 15-minute interval. Question number 12. How can you generate a random number between 1 and 7 with only a die? Any die has 6 sides. From 1 to 6, there is no way to get 7 equal outcomes from a single rolling of a die. If we roll the die twice and consider the event of 2 rolls, we now have 36 different outcomes. To get our 7 equal outcomes, we have to reduce this 36 to a number divisible by 7. We can thus consider only 35 outcomes and exclude the other one. A simple scenario can be to exclude the combination 6 6. We can exclude 6 and we will get 35 outcomes, that is divisible by 7. Roll the die again. It appears, if 6 appears twice, all the remaining combinations from 1, 1 till 6, 5 can be divided into 7 parts of 5 each. This way, all the 7 sets of outcomes are equally likely. Question number 13. A certain couple tells you that they have 2 children, at least one of which is girl. What is the probability that they have 2 girls? To determine the probability that the couple has 2 girls, given that they have at least 1 girl, we can use the conditional probability. So here we will use conditional probability. Let us consider the possible combinations of gender for the 2 children. It would be boy boy, number 1 boy boy, number 2 boy girl, number 3 girl boy, number 4 girl girl. We know that at least one of the children is a girl, so we can eliminate the first possibility, that is boy boy. We know that one child is girl child, so we are left with 3 equally likely possibilities, that is boy girl, girl boy and girl girl. Since the gender of children is independent, the probability of each possibility is 1 by 3. Each possibility has a probability of 1 by 3. Out of these 3 possibilities, only one corresponds to having 2 girls. Therefore, the probability that the couple has 2 girls, given that they have at least 1 girl, is 1 by 3. In the summary, the probability that the couple has 2 girls is 1 by 3. So 1 by 3 would be answer. Question number 14. A jar has 1000 coins, of which 999 are fair and one is double-headed. Pick a coin at random and toss it 10 times. Given that you see 10 heads, what is the probability that the next toss of that coin is also a head? To solve this problem, we can apply Bayes' theorem. So here we will apply Bayes' theorem to calculate the probability that the next toss of coin is head, given that we have observed 10 heads in a row. We have observed 10 heads in a row. Let's define the event. A. The selected coin is fair coin, 999 out of 1000 coins. B. The selected coin is double-headed coin, 1 out of 1000 coins. C. Observing 10 heads in a row. We want to find the probability of event B. Next toss is head, given event C. Observing 10 heads. So Bayes' theorem, this is Bayes' theorem, formula for Bayes' theorem. So PC by B is probability of observing 10 heads in a row, given that we have the double-headed coin. Since the double-headed coin always results in head, that is PC by B is equal to 1. So probability of B is the probability of selecting double-headed coin, which is 1 by 1000. Probability of C is the probability of observing 10 heads, which can be calculated as follows. PC is equal to, here we apply Bayes' theorem. PC is equal to PC by A, probability of C by A, into probability of A plus probability of C when P has occurred, that is P C by B into P probability of P. Probability of C would be 0.5 to the power 10 into 999 by 1000 plus 1 into 1 by 1000. Now we can substitute the values into the formula. PB by C is equal to 1 into 1 by 1000 by 0.5 to the power 10 into 999 by 1000 plus 1 into 1 by 1000. So we can calculate the expression value of and we will get our answer. Question number 15. What do you understand by statistical power of? How do you calculate it? Statistical power also known as sensitivity. What do you understand by statistical power of sensitivity? How do you calculate it? Statistical power also known as sensitivity is a concept in statistics that measures the ability of a statistical test to detect a true effect or difference when it exists. It is probability of correctly rejecting the null hypothesis when it is false, indicating the test ability to avoid false negative. The statistical power is influenced by several factors, including the sample size, the effect size, the significance level, alpha, and the variability of data. A higher statistical power indicates a greater likelihood of detecting an effect if it truly exists. To calculate the statistical power, one typically needs to determine the sample size, the desired effect size, and the chosen significance level. The specific formula for calculating statistical power may vary depending on the statistical test being used. Sensitivity is commonly used to validate accuracy of classifier, logistic, as mean, random forest, etc. Statistical power can be calculated using statistical software, online calculators that provide power analysis for different study designs and statistical tests. These calculators typically require inputting the relevant parameters such as sample size, effect size, and significance level to estimate the statistical power. It is important to note that the statistical power is not an inherent characteristic of a dataset or analysis, but rather a property of the test being conducted. Higher statistical power is desirable, and it increases the chances of detecting true effects and reduces the likelihood of